Hi, this is Scott Vaughn. In this video, I'll look at exponential regression and I'll do a comparison between what the TI-84 does and a regression produced on Desmos. And I'll say that it took a lot of energy to get back to making a video about exponential growth. I really don't want to look at exponential functions right now, as I suspect many people don't. And I'm a math teacher, but I think we can use the data that we're all looking at with the exponential growth in the number of cases to study log functions, which are inverses of exponential functions. And so we can learn a little bit about log functions and how regressions are done both on the 84 and on Desmos, and compare them and learn a little bit about log functions and the properties of log functions in the process. I'm recording this on April 2nd, 2020 at home, and there's my daughter in the background doing her schoolwork at home also. Okay, so here in Excel I've listed days through March. So this is March 1st and March 7th up to March 31. This is the number of coronavirus cases in the US, and this is the log of that number of cases. So I had already worked on some videos where I downloaded and copied all of the data for the entire month from several different countries and pasted it into Desmos and analyzed it, but it all got just too depressing and scary really to think about all of that. So what I'll do here is just look at these few data points that are something that I can also type into the calculator, and that's what I'm going to try to accomplish with this video, is comparing the results on the calculator the way we would have done it in class, where you normally have the calculator in hand and you analyze the results from the calculator and compare the results that we get in Desmos, and that process in Desmos will help sort of illustrate what the calculator is doing. So I thought that was what was particularly useful here and my main goal in this video. So maybe one of the things I can say about the log function is it sort of gives us a way of managing these large increases in the number of cases, right? Because when you take the log, what you're really doing is saying what exponent would you need. In this case, because this is log, this is actually the log base 10. So I'm saying log of cell B3, so log of 98, and using log instead of ln, I'm doing base 10. And so what that means is we're calculating what number or what exponent would you raise the power 10 to get 98. In other words, 10 to the power 1.99 is 98, and 10 to the power 2.7 is 518. Of course, I could just comment that obviously 10 squared is 100. And so this is very nearly 10 squared, right? And maybe, like you could say, 10 to the third power is 1,000, but this is 10 to the power 3.67 roughly is 4,632. And then, so this is on the order of 10 to the fourth and 10 to the fifth. 10 to the fifth is like 100,000. And this is 10 to the power 5.33 roughly. That gives me this 213,000. All right, so that makes the increases a little bit more manageable in keeping track of, and you can see that very visually when you type these values into a calculator or into Desmos. Let's type them into Desmos first. So this is Desmos.com, and we can start a new graph here. Let's type in those values that we just saw. Okay, so now that I have that data in, I mean, the first thing that's happening here is that we can't see any of these data points. They are completely off of the scale that is the default scale here. And if I zoom out, you can start to see the data points showing up. But it's obviously that this sort of default scale here is just not practical for this data set, right? So there's, of course, we could reset the window. But what's useful here is to actually graph the log of these values. And so actually Desmos provides a pretty neat way you can do that. I can just type x1 comma and then log of y1 and just have it plot those values. Now that shows up in a range of up to about 5, right? Because we're going up to 213,000 there, and there's a nice manageable picture of the increases in the number of cases, recognizing that this is the number of days across the horizontal scale, and the vertical scale is the log of the number of cases, base 10. All right, but now to try to stay focused on what the primary goal for this video is is comparing the regressions on the TI-84 and on Desmos. And so let's also put the same data into the calculator and look at that. So to do that, you'll hit the stat button, and want to edit, so hit enter, and we've got these columns here. L1, I'll put the day, the number of the day, so type that in, and the number of cases in L2. Okay, so once that's in, you can exit from that, so second quit, and then of course looking at the graph we don't see anything because this is the standard window from -10 to 10 and -10 to 10. All of these number of cases are completely off the window, so we can reset the window. Let's click on the window button here, and let's go from 0 out to, on the horizontal scale, the x values, let's go to 35 because we've got 31 days here. And the x scale means how many hatch marks it will make between 0 and 35. So we'll do one every unit. So it'll count 1, 2, 3, 4 out to 35. And then for the y minimum, let's go with 0 up to, let's say, 250,000 for the upper limit here for the window. And we could count by any number here. Why don't we count by 50,000? So we'll take a look at the graph this way, and actually I don't see anything because let me make sure I have this cleared out. There's no function in there. Actually what I'm plotting is stat data. So you see it says stat plot right above the y equals button, so I have to go to that. So I'll go second, stat plot, and then I want to turn plot number 1 on, so I'll just hit enter. And I want to use L1 and L2 as my x and y values, and just use a scatter plot, so I need to turn that on by hitting enter. Okay, exit from this menu and now go back and look at the graph, and there are the data points that I just entered in. And what we'll do now is to find a curve that is the curve of best fit, what's also called a regression. So I'll just take a moment to explain that term regression because I think it's pretty fascinating. One of the earliest places where this math was done was in astronomy and tracking the positions of stars and planets. And at the beginning of that science, the tools, the telescopes that were used, were not as good as they are now, of course, and so there was a lot of error in the data. Of course, the errors, because the tools were not that great, and also there's all sorts of atmospheric interference in measuring the positions, and so there were these mathematical and scientific models of where the planets should be that were the ideal mathematical values, but then the real measurements were off from those mathematical ideals. But with more and more data, that data would move toward the mathematical idea. And so in a sense, these values regressed toward the ideal values. And so that's where the term regression comes in. We use that term all the time now in finding these curves of best fit. So either you can just refer to a curve of best fit or a regression. And because this data is growing exponentially here, we'll find a regression, exponential regression, or a curve of best fit for this, and use an exponential model. So on the calculator to do that, I'll go back to stat data, and I'll do a calculation. So I'll just move over 1 here and then look through these regression model options. So this is the kind of scientific decision that we would make as to which one of these seems most appropriate for the given data, and we'll choose exponential regression sort of based on the scientific analysis here, and then the mathematics will produce the curve that is the best fit for that data. So hit enter on that option for exponential regression if that's what we're going to decide to model it with. Gives us the options to choose which input and output, and I could store it in the Y editor. I think I'm not going to bother to do that right now. I'm just going to ask it to do the calculation, and then I'll just write it down what we get. So we get an A value of 84.6 and a base for the exponential function of about, let's say, 1.3. So let's just write that down so we can compare it with the results in Desmos. So just rounding off the values, what I get from the calculator, we are looking at a model that says the starting value at time 0 is 84.6 in the model, and it is growing at 30% per day, compounded daily, according to this model. Let's do the same thing in Desmos and look at what model it produces. Right, so I'm just comparing again to make sure that I have exactly the same data here. And yep, both columns are the same. So what does Desmos produce? When we do request the same thing, we'll say Y1 to do a regression. Y1 based on the values I have in column Y1 there. Y1 we'll do an exponential model, A times B to a power, and we'll use X1, the X1 data. So this model is different, and that's what I'm going to try to explore and explain why it's different. Let me back up so we can actually see that data. So we need to reset the window here. So let's go from 0 out to, let's make this the same window, 35. And then on the vertical scale, let's go from 0 up to 250,000. Okay, so Desmos produces this result. It's a different result. It says that at time 0 we have 767, and we're growing at about 20% a day. And I will explain why Desmos is getting a different result. I mean, kind of the part of the answer will involve, obviously, this little checkbox here is interesting to explore, and that's precisely what the calculator is doing. And so the rest of this video, I'll be going through and kind of explaining what is this log mode. You can click on the question mark here and read and learn about that. It says, when log mode is enabled, a transformation that makes the model linear is applied to both the data and the model before fitting the parameters. And it can be used when you're doing regressions of these different types. So I'll explain what that really means. I can go through some visuals and do some properties of logs to explain really what that actually means. And another thing that's pretty neat, what Desmos provides here is, I think, well, it doesn't really matter. Either way, you have this option to graph these residuals, as Desmos calls it. And what that does is it's plotting values that tell me basically how far above and below this curve of best fit is to the given data points. So what Desmos has done is go through here and find a curve that minimizes all these little deviations, or minimizes these things that are referred to as the residuals. I wonder if those will change, whether we include log mode or not. I think what's happening now, I can see actually now it's included a column up here for the residuals. So they're graphing in green, which is a little confusing. See if I can change that color. So the curve of best fit is in blue, and the residuals are graphed as these little black dots. And they are above and below the x-axis, indicating whether they are positive or negative. See, this one is negative because the actual data point's below the curve. This one is positive. It represents the distance at which this point is above the curve. And so the Desmos is going through and minimizing all of these residuals, finding a curve that minimizes the residuals. I'll talk a little bit more about that as I get to later in the video, because this is a topic that we can explore in depth in Calc 3, but that's a whole nother story that I'll just hint at a little bit later in this video, exactly how it goes through and minimizes them. Right now I just want to explain that that's what it's doing. And that's true in both of these different plots. And staying really on my primary focus here is how does it, what's the difference between these two different modes, whether you have log mode or not? And it's now, as you can see, it's the TI-84 that produces this curve of best fit. So how does it get that? That we can explore where that comes from by looking at properties of the log function. So I'll do that now. And if I didn't make that point clear enough, maybe I'll just emphasize it one more time right now, that what we mean by a curve of best fit is a curve that will minimize all of those residuals. Ultimately, that's what it's about. That is a complicated process if you want to see the inner workings of how that happens. That's actually a topic in Calc 3. I'll come back to it, but we're finding a curve that minimizes the residuals. Okay, so comparing the two different models, the one from the TI-84, we had an initial value 84.6 and a growth factor of 1.3, which means 30% growth per day. And on the Desmos.com, with the standard default exponential regression that it produces initially, we have an initial value 767.2 with about 20% growth per day, or a growth factor of 1.2. And Desmos is really pretty versatile because it really gives us the option for either of those two models. So with log mode turned on, we're getting what the calculator produces, and now we can actually use Desmos to look at how this model is generated. So then I'll go back to the original data, and I'll just take the day values, and I'll take the logs of each of the number of cases. I'll take that data and plot that in Desmos. So now what we'll do is we'll get a line of best fit for this data. These are the logs of the number of cases, log base 10. So to get a line of best fit, what we could do is look for the slope. So we'll do mx plus b form. So I'll say y1 approximated by a line with slope m. I'll use x1 for the x values, plus, and I'll call this b1 just so we don't confuse it with b that represents some growth factor. So b is the y-intercept for this line. This is the line of best fit. It's the line that we know is minimizing all the residuals. Actually, we could plot those residuals here. And so they are the distances above and below the actual data is from the line. And so the line is called the line of best fit because it minimizes all those residuals. So what I'm doing here is finding a linear model for the log base 10 of all of those y values, of the original number of cases. We take the log base 10 of the number of cases and plot that and find a linear model, a line of best fit for that data, and we get this is the slope of that line and this is the y-intercept for that line. Let's write that down. We're looking at a linear model that has this form, slope and y-intercept, and I'll call that b1 for the y-intercept for this y1 model. And the slope that we just found is about 0.1142, and the y-intercept was 1.9275 approximately, rounding off in both of those actually. Now if we're going to find an exponential model based on this line, what we could do is say our exponential model, we'll call that y2, and say it has this form. So what I'll do is I'll say, well, if you took the log base 10 of both sides, it would still equal, because log is a one-to-one function, so log of both sides looks like that. And then we can use properties of the log function on the right-hand side to rewrite this. So let's say this is the log of y2 equals, and the first property I'll use is that log of a product, you can split that up. So we'll say log of a plus the log base 10 of b to the power x. And then it's another property of the logs that x value, that x factor, can go in front. This is the log base 10 of y2 would be the log base 10 of a plus x times log base 10 of b. Now I'll just rewrite that where I put this first. This is actually the slope of a linear function. So we'll have log base 10 of b, let's say, times x plus log base 10 of a. Now this is the slope, m, for a line, and this is the y-intercept before that I called b1. So this is the slope, and this is the y-intercept for the line of best fit. And what did we have actually in the line of best fit? We had a slope. That slope was 0.1142. And the y-intercept, the b1 that we had in the line of best fit, that was 1.9275. So what I'm going to do is say this is the log of b, and this is the log a. In other words, log b is equal to 0.1142, and that's base 10 log, which means we can rewrite this as 10 to the power 1142 is b. And you put that on a calculator, 10 to the power 0.1142, and you get about 1.3. For the growth factor, the base of the exponential function is 1.3. And over here, when I know that the log of a should be 1.9275, that means 10 to the power 1.9275 is a. And this is going to be about 100, 10 to the, about 100, 10 to the 1.9, that comes out to be 84.6 for the a value. So that's how you can track back if you now know what b is and what a is for some exponential model. We can go back and look at what the a and b would be in an exponential model, because we found the corresponding slope and y-intercept when it's written in a linear form. So we know that this y2 has this form a b to the x, which means it's 84.6 and 1.3 to the power x. So just recapping, what we just did there was we just found this line of best fit. Found the line of best fit, we found the slope and the y-intercept, and figured out what the corresponding initial value and growth factor would have to be for a log model that had this that's written in this form. So that's how we could extrapolate back from the line of best fit for the log of the data. We can figure out what the corresponding exponential model would have to be. So we're first fitting the line of best fit to the log of the data, and then using that to extrapolate what an exponential curve would be that would correspond to that. So that's what Desmos provides as an option, and that's what the TI-84 does by default. Well, it's not only what the TI-84 does by default, it's the only thing that the 84 does. And so actually now when I get to the Calc 3 class, I can go back there and say that it's even when we're working out the line of best fit for data that's linear like this, we can then use that result for finding exponential curves of best fit. So that work in modeling linear data is useful also for exponential data. On the TI-84, when we plot data that looks like it grows exponentially and we ask the calculator for the line of best fit, the calculator gives us this, if we round off, 84.6 times 1.3 to a power x. And if we look at that graph, that's a good fit to that data, and that is a best fit based on taking the log of the data, as we see here in Desmos, finding a line of best fit for the log of the data, and then using this slope and y-intercept to determine the corresponding value a and b for the exponential, these values a and b that I have here. And that's what the calculator does. We can see that now is really illustrated using Desmos. So I thought that was pretty cool, worth taking a few minutes to look through and think about the inner workings. I'll just use that metaphor one more time about how a lot of times when you're driving the car, you don't really think about how the engine works. You don't really want to. You can't spend time thinking about how the engine works. But every once in a while, when we're doing math, what we're really learning is every once in a while it's useful to know how that engine is working. Maybe it breaks down, or maybe you want to improve performance. And knowing the inner workings of these engines here can be valuable. Now, maybe you're left wondering, which of these two models is the correct one, or at least the best one? Well, if we're talking about a question on a test or homework problem, the answer is it all depends on exactly the wording or assumptions made in that test or homework question. And that's really ultimately an important lesson about mathematics in general. What we're seeing here is two different conclusions based on two different possible assumptions we could make at the outset. In math, the work that we do is always about taking whatever's given, whatever definitions or assumptions or established principles are known to be true, and then following those givens to a logical conclusion. We can find a curve of best fit that minimizes the residuals or deviations between the curve and the data at the outset, or we could first take the log of the data, find the line of best fit for the log of the data values, and transform that back into an exponential function. This is sort of like looking at the data with two different filters, or with two different lenses. Which one is better? Well, another way to answer that question is of which of these models is better from a scientific point of view is to see which is better at predicting future data values. And that's what science is about, and that's how science can use mathematics. All right, I guess that's the end. Thank you very much. I hope it's been helpful and interesting, and thank you for watching.